the basic idea behind Bayes' rule. Okay, you have the chance of observing A given B is P of B given A times P of A divided by P of B. And then your questions that you had 2 weeks ago, Devin, were actually really relevant because most of the time when people read these things, it's actually difficult to kind of map this to what you would actually do in real life with actual data. So what this actually means, so A in this case are basically your model parameters. So like if you're doing something like linear regression or anything else, which has some sort of number that you feed into it, that's basically what A is. And so B, we'll do this. Question?
I was going to say, is B just the observations, like the data?
Yeah. Data. Yeah. And so, right, so you'd call this then posterior. So basically X, like when we say we define X, like that's basically what B is right over here. All right. And so this is what you call the posterior. And this is basically your final answer. Like when you're done solving a Bayesian problem, you have your posterior. And then the idea is A are basically statistical distributions. Like this is like kind of something we had a difficult time with last time. Bayesian models don't deliver point estimates. They deliver simulated distributions. You know, 5,000 or 10,000 or 1,000 different, you know, samples that are generated for you. And so the idea then is if your model has, let's say, like 13 different parameters, you'll actually result in 13 different simulated statistical distributions. And so that's actually what A is in this case. Like that's what you're solving for.
It's a distribution of probabilities?
Yeah, exactly. That's exactly what it is. No, so what it is, it's a collection of distributions, one for each of your model parameters. So the idea is, like, so we've been talking about linear regression. So like if you have 13 columns, you have 13 different coefficients. And so normally if you solve linear regression, you might say the coefficient for XYZ column is, you know, some number. But with Bayesian modeling, it's actually a distribution with, let's say, you know, 1,000 or 5,000 samples. And then the average value of that distribution would basically what you would report your coefficient as.
But isn't there one answer for like what minimizes some error term?
Yeah, and so that's essentially what it is, more or less. And keep in mind too, so when you solve something analytically, like traditional linear regression, that's sort of what you're doing. Like you're kind of basically performing some sort of closed form solution which analytically solves some sort of loss function which minimizes it exactly. So another term for Bayesian modeling, I'll write it up right over here, is it's also called probabilistic modeling, right? Because what you're done with is, you know, like a bunch of probabilistic data. And then also another word that you hear sometimes is called generative modeling. Okay, because the whole point is when you basically feed things into a Bayesian model, you're not explicitly minimizing some sort of objective function like you are with most machine learning techniques. You're just literally what you're doing is just generating probabilistic data according to some sort of predefined set of assumptions that you defined beforehand, like up here. All right. It typically is the case that your results will more or less be the same, but they're, in terms of how and why they operate, they're kind of defined to sort of perform, like mechanistically, they do different things to arrive at their answers. So I guess for a Bayesian model, you're not explicitly minimizing some sort of loss function. You're just defining some sort of data generating process and then just sampling from that to arrive at your answers. But it's generally true though, like Bayesian models only work with statistical models that have some sort of underlying statistical assumptions with them. And so it's usually the case solving things analytically, like we did in the DAT class, versus doing them in the Bayesian way will more or less give you about the same answers. Because the idea is, you know, the reason why we can define linear regression in a Bayesian manner is simply because you can actually define linear regression in terms of different types of probabilistic assumptions. Like that's actually how it sort of arrives at its answers in the first place, because it has these assumptions that things fit normal distributions and so on and so forth. So it doesn't. It doesn't solve anything in terms of minimizing a cost function. But because the way linear regression works itself is by sort of satisfying these statistical assumptions, you can sort of start with those statistical assumptions and then sample from them to generate, simulated draws for your final parameters, and it'll be about the same. All right, how's it going?
I sort of get it.
Okay. Now, the idea is generative modeling is just, it's not about arriving at a single precise analytical answer. It's just about generating synthetic data to mimic some sort of underlying relationship which drives the observations that you're trying to figure out.
And when you say sampling, like, does that mean, like, let's say you feed it a data set of like 10,000 observations, like, does it sample like, 100 at a time or something and run through different, is that what it's sampling, or is it sampling like different parameters?
Yeah, it is essentially. So let's just kind of go on for a few more steps here, okay?
Okay, yeah.
All right. Yeah, all right. So this is kind of an ugly screen here. I'll start a new one. So the idea then, all right, so we have, okay, like this right over here. All right, so the idea thing, so this thing right over here, PV of A, okay, is what you're doing over here. This is called the likelihood. Okay, and this right over here is basically what generates Y. Okay, right over here. And then this, priors. Okay, these are distributions for model parameters. So the idea is, what do you sort of expect the coefficient values to be beforehand? Okay.
Gotcha.
All right, and so the idea then, you actually use the data in X, right, to generate these values right over here. Okay, so like basically however your model makes its predictions is what you actually use right over here to go ahead and then arrive at some sort of answer. And then the bottom right over here, like this, okay, this priors likelihood, this has a less defined name, but it's called marginal distribution. All right, and so what you're doing, okay, is you're trying this. You're basically what you're trying to do is actually let me backtrack. So you mentioned before, Devin, about not being able to solve things analytically, like in terms of minimizing something like very, very precise. So this is Bayes' expression right over here. And then the basic idea here is that for most modern problems that we actually want to use Bayes' rule for, there's not a single precise answer. So I actually spoke maybe a bit too quickly here when I mentioned that like you don't actually solve things analytically. If you have a very, very simple problem, you actually can solve this exactly to arrive at a very, very precise answer. But almost any sort of problem that you would actually want to solve in real life, like any sort of data set of any sort of significance that had more than one column, then you would probably not have an exact answer to this. So the sampling is basically a way of estimating what this expression would evaluate to without actually solving it analytically. So essentially what you do then is you use a step technique. This is what you call Metropolis Hastings, which is sort of where you start with very, very naive estimates for all these values. So we might say like, A right over here is a distribution, of mean, right? Normal distribution with average 0, standard deviation 1, which is like the most typical distribution you can kind of start off with in the world, right over here. And then this, right, is just kind of whatever process is used to generate y. And then down here is usually a very ugly expression which can't be solved precisely. And so essentially what you do is you start with you just kind of start off with whatever values you define for these right over here. You essentially generate a number, okay, like from whatever so you just sort of you plug your different distributions into this expression right over here. You take whatever sort of number arrives, like this, and then essentially what you do is you have some sort of threshold. And so what you do then is you would basically randomly generate a number from this expression right over here, okay? And then you would do that a second time, okay? And then the idea is if the differences between the first simulation and the second simulation are different, then you map basically the new values of your distribution to the, actually, let me make sure I'm not talking too much here, Devin, okay? One second. All right, let me go ahead over here. All right, because the sampling, okay, let me write it down again. I'll try and do it smaller. Okay, yeah, so literally, right, you actually define all of these values as being some sort of underlying distribution. Okay, and so essentially what the basic step works, so basically the sampling goes, is, right, you define beforehand what you think these values are going to be. Okay, like you could say you think your model parameters are going to be normally distributed, or a t distribution, or a Poisson, or a y-bolt. There are like 30 different distributions you could choose from, or whatever, right? So
the parameters themselves are just, you're talking about the distribution of the parameters?
Yes, correct.
Like if you have 10 columns, for example, you have like 10 parameters?
Yep, exactly.
Oh, huh, okay.
Yep.
I've never thought about the distribution of the parameters themselves.
Yeah, no, you don't actually, typically you don't really think about it that way, right? It's kind of, you sort of naturally think about these things as maybe being point estimates, like kind of being a single number. But literally, no, you define these things as sort of being statistical distributions that you sample from. So the idea is, let's suppose if you have a column, right, we'll just call it over here, X and Y, right? And then you have, some numbers right over here like this, things along those lines. And so if you were to kind of run univariate linear regression, you might be able to say something like this: y is equal to 2.4x plus, whatever the intercept is. Let's just, I don't know, we'll just call it b for now. Okay, so the idea is this 2.4 right over here is actually proportional to some sort of distribution, like a normal distribution, a t distribution. We'll call it normal for now. And then the idea is the average value of that distribution is 2.4. And then there's some sort of, standard deviation of that, which could cause this number to fluctuate a little bit.
I see. Yeah,
But it is the normal distribution with this parameter right over here is what's actually generating this number.
Right.
Does that make sense?
Yeah, that makes sense.
Yeah. So that's why you kind of, so you start off with your pre-existing, basically what you believe the distributions to be.
Right.
Things like that. And then you solve this. And then what you do is you have what the distributions of these things actually are given your data.
Right.
Yeah.
And it's distribution you're sampling, like it's not the true population that you're looking at?
No. So essentially what you're doing then is you typically start off, right? You might say, we believe A is, you'd normally say something like it's a normal distribution, 0, 1, or, a t distribution, things. Basically, different types of observations have some sort of underlying statistical process which drives them, and so distributions have, different types of parameters. So t distribution, same thing, has kind of like an average value and then a standard deviation with it. If you're observing maybe something like attendance, Like, so attendance, normal distributions can be negative. A distribution which can never be negative is called Poisson.
Yep.
Right? That's like count data, you know? And so you could say, if you think maybe average attendance for a particular locale, whatever, is maybe 15, you know, things along those lines, you could pretty much say, you know, Poisson distribution, like with the rate parameter 15, something like that. But essentially, you define some sort of distribution which sort of defines the model parameters that you're trying to figure out for.
Gotcha.
Yep. So the idea is you start off with some sort of pre-existing belief about your model parameters, and then when you're done applying it to your data, you have new model parameters which are better informed. That's basically the idea. Cool. So you have distributions going in and then distributions coming out. And then the idea is the distributions coming out are less naive than what you started.
Gotcha.
Okay. All right. So you're saying like you're like some things have become a bit more clear.
Yeah.
Okay.
It's pretty clear. Yeah.
All right. Okay. All right. So that's the basic idea then. And so the sampling that you do, the basic idea behind it, I'll just keep writing this over and over and over again. Okay. So generally speaking here, Devin, are you, obviously you're at a computer, right? Okay. Let's go ahead and just type something in here. It's called conjugate priors. Okay. Like if you were to take a graduate class in Bayesian methods, you actually spend quite a bit of time talking about these and things along those lines. We're going to try and skip to the main point. So Wikipedia, go down to this table right over here.
Yep.
Okay. Okay. So this is the complete list of different types of distributional assumptions, which will give this expression a precise answer.
Okay.
Okay. So what this means is, if you kind of go through over here, so the likelihood, this thing, right, the data generating process, which is this step right over here, if you believe this is Poisson, and then if you set up the prior distribution, okay, to be a gamma right over here, like this, okay, then essentially what this means is the posterior, you can solve exactly by figuring out this expression right over here.
There's no other parameters. It's just the distribution type.
Correct. Correct. So actually what this means specifically here, Devin, is if these things sort of, if you define these different expressions, right, you say this is Poisson right over here, and then this is gamma right over here. And this is also critically important. If there's only one of these parameters, so not 2, not 3, not 4, not 5, you know, things like that. Right. So if it's really just literally just a single distribution over here and then a single distribution over here, then the corresponding distribution, when you're done, you can figure out just by plugging the numbers into these expressions right over here like this. Okay. And what's actually really important here, Devin, is this is only really for univariate problems. Right. So essentially, imagine like if you had maybe right, a data set with just one column.
Right, right.
And so therefore you thought that one column followed a gamma distribution. And so therefore, and then you thought the interaction between you know, A and B followed a Poisson distribution, then you could have one single distribution at the end right over here. The thing is though, is that once your data set goes beyond one column, then P of A right over here isn't just a single distribution, but it's multiple ones.
Right.
All right. And so then in practice, then this expression basically can't be solved directly.
Right.
Okay. So this is kind of the exhaustive list of Bayesian problems which have precise answers, and everything else you have to estimate it.
Right. I guess the one part I'm still not quite getting is like how do you generate this distribution? Like what? Like a distribution makes sense to me when you have like data or observations, you know, that you
Well, keep in mind the likelihood right over here.
Uh-huh.
The likelihood is actually what incorporates X, your actual data itself.
Mm-hmm.
Okay,
Right.
so the likelihood
Yeah.
is actually what kind of allows you to take your distributional assumptions and actually have them interact with the data itself. So,
Right.
for example, here, so let's use linear regression as an example. Okay,
Uh-huh.
let's just do simple columns: x1, x2, x3, and then we have y over here.
Mm-hmm.
Okay, so in this case, right, we kind of know linear regression is basically something like y is equal to coefficient 1 times x1 plus, coefficient 2 times x2
Mm-hmm.
plus coefficient 3 times x3. Right? Like that's how you generate y
Mm-hmm.
right over here. Okay. So this right over here, so like if you're doing linear regression, right, this is the likelihood.
Right.
Like that's actually what generates the predictions. And the idea is these things are your model parameters, right?
Right.
Okay. And then this is your actual data. Like
Right.
those actually like that's your real world data over here. And so the idea is the way you actually sort of sample data from something like this, right, is what you do. And this is literally sort of how linear regression is defined, like sort of in a very, very formal way.
Uh-huh.
What you say is y is proportional to a normal distribution.
Mm-hmm.
Okay. And then the average value of that distribution
Mm-hmm.
is the answer generated by this right over here.
Right.
Okay. So whatever answer that you would get from like adding up these things right over here, you assume, right, that's essentially just the center of some sort of normal distribution.
Right. Right.
And then
Okay.
the standard deviation right over here is
Mm-hmm.
basically this is actually derived from your error column.
Uh-huh.
Okay, so when we say, y is equal to m1 x1 plus m2 x2, plus b, whatever, we assume the actual, like the variation of that answer basically follows a normal distribution. And
Mm-hmm.
then this just sort of represents the most likely sort of sampled value from that.
Mm-hmm. So basically, then the distribution comes from solving the linear equation for each observation, and that gives you data points to put in the distribution.
So the way you actually sample it in sort of a Bayesian sort of way,
Mm-hmm.
okay, is remember we start off with prior distributions for A. So in this case, like M1, M2, M3, we say we think these things are normally distributed, with X, Y, Z parameters, things like that.
Uh-huh.
And then essentially what you do okay. Okay, so we basically have something like this. Okay, and so essentially the way you solve this, right, is sort of right? So whatever expression you use to generate the predictions,
Mm-hmm.
right? And then sigma right over here. So this thing corresponds to that. Okay, so this is its own distribution, which is just the combination of your coefficient values multiplied by your data. And so P of A,
Mm-hmm.
right? This is basically, let's suppose we have two columns in our data, okay? M1, M2 right over here. Okay,
Mm-hmm.
we could say this essentially. Okay, so sort of the way you actually sort of sample from this, Devin, is if we had two columns in our data set, we would sample two values from this corresponding distribution right over here. Okay, then we would plug them in right to this expression right over here. Okay, and so essentially what we would do then is we'd sort of have right this value times this one, and then this value times that one right over there.
Yeah. Okay.
Okay, you know what I mean? So that's sort of how we actually sort of, starting off with distributions,
Right.
kind of define what our model is, and then we actually sort of generate like random numbers from that.
Right, right. Okay, yeah, that makes sense.
Okay, and so basically what you do then is you just kind of do this over and over and over and over again. And then what you sort of do is you sort of, all right, so step 0. Okay, you just kind of sort of randomly draw, right, like from these values right over here and plug them into these expressions, okay? And then you get some sort of answer, right? So if you were to go ahead and kind of solve this right over here, you'd actually have 2 numbers, right? Like you'd have, because, you know, you have a number here, 2 numbers for P of A. You multiply each one, you know, by this expression right over here, like the whatever generates your observations. And then essentially, right, you have number 1, number 2 right over here. Okay, and then you do this again, right? And then you just have a second set of numbers, okay? Like this, all right, so we'll just call this, okay, N3, N4. And so basically what you do then is after every single step, okay, you just compare the differences between these two, okay?
Okay.
All right, so essentially you just sort of look collectively, the difference I believe it's going to be this right over here, N1, N2. Okay, so you look at the differences, right, between this number and that number right over here. This is equal to some sort of value, okay? Like, I don't know, whatever we call it. Okay, so some sort of difference, delta, okay, like that's usually commonly used right over here. And so the idea is what you have is some sort of threshold that you use, maybe something like 0.1. Okay. So the idea is if the value of delta is greater, let's say you can actually set this to kind of for yourself. Right? You know, this is a number you define. And so basically, if the differences between the old values and the new values is above some sort of threshold, okay, what this means is this value right over here becomes the new value here. And then this value right over here becomes the new value right over there. And so you actually use that to update your distributional assumptions. And so essentially what you kind of do is you kind of sort of do like a little bit of a pathfinding sort of technique where you kind of basically go in the direction where there's the greatest change. And so the idea is eventually you might just do this after 5 or 6 or 7,000 times. And then at that point, basically until the differences between the number from your current round and the number from your previous round basically never goes above this threshold. And then at that point, the idea is you sort of settled on kind of what the true values of these things are. And that's basically what P A of B is right over here like that. And so that's how you sample. So basically, you kind of plug in numbers into these distributions that you define. You sort of generate the new values, you compare new to old, and then if the differences between new and old is above some sort of threshold, the new values basically become the new estimates that you put in right over here. And that's basically what your priors are. That's basically what your answer is. And so when you're done, these are your posterior distributions. And so the basic idea is if you do this long enough, eventually you'll kind of find out what the true values of these things are, given your data.
Gotcha.
So it's a way of sort of, it's almost a universal method of kind of just guessing what these two true distributional values are, given the data that you already have. And then the idea is if you sort of run enough simulations, you'll eventually kind of arrive at the correct answer. That's basically what the sampling techniques are. And so essentially then, every single time you run through this process, that generates, that's sort of the generative part of it. Because what you do then is you basically generate, these new estimates for what your distribution is, and then you log them. Okay. And then by the time you're done, if you ran 10,000 simulations, you'll have a collection of 10,000 different numbers for what these distributional values are. And that's sort of what makes up your posterior distribution over here.
I see.
Yeah.
Cool.
Interesting, right?
Yeah.
Yeah.
That's cool.
Okay. Yeah. All right. So that's it right over here. Just for whatever it's worth here, Devin, we haven't really talked about it. So this is likelihood. This is the prior. This thing down here, P of B, is actually the most difficult thing to calculate. And that's actually why most of the time you can't solve it analytically, is because what goes down here is actually too complicated to solve by very traditional means. And it's why you have to use the sampling techniques. And then this is actually computationally fairly expensive, because basically every single draw you have to do, you kind of have to perform some matrix operations to generate, these values. And so until like 2005 or 2006, Bayesian methods were kind of interesting theoretically, but they weren't really practical in any sort of real sense. But now that's changed, and things like that. And so now it's becoming more popular. Okay. And so then when you're done, right, you have some sort of distributional inference for what your true model parameters are. And it maybe gives you a better way of thinking about a range of outcomes. Yeah. So basically, anytime you need probabilistic inference for your answers, which is actually fairly common in business outcomes, Bayesian methods tend to be pretty popular. But they're kind of difficult to get your head around. It's not. It's not immediately clear how things work. And then getting things set up is also cumbersome, because you kind of have to understand what's driving your model and things like that. So it's not like you can just kind of mindlessly plug and play things. You kind of have to have a lot beneath you before you can kind of make use of it in different ways. Okay. But this is basically what Stan does, or rather what Prophet does when it generates its forecasted predictions.
Right.
Like, it actually goes through this, and it does a sampling technique to arrive at these values. And so basically for Prophet, the model parameters that it's trying to figure out are things like the weekly and the daily and the monthly and the yearly effects in your time series. And so therefore, if it's a Monday, right, you might say increase the expected value by 6.7. And so really that number 6.7 is, it actually is a normal distribution, with an average value of 6.7 and then, a standard deviation of whatever.
And it does that for the trend too, or just the?
Yeah, everything.
Cool.
So things like the trend, monthly, basically every single parameter that it uses to create its prediction is basically the result of, the default is to go through 1,000 simulations of this process. And then it just takes the 50th percentile of the numbers that were generated as kind of like to make its predictions.
And it does that for each date, or does it over the whole data set?
Does it for every single date.
Oh, wow.
Yeah. So when you're done, you'll actually, so for example here, the one example we were going to look at is a time series that has 2,905 observations. And so the idea is for each one of your model parameters, right? So things like the trend or, the weekly, things along those lines, you'll actually have 1,000 different simulations for each one. And so therefore, so regardless of what you're trying to look at, so maybe, the expected value of, some sort of observation, or, the true value of, the seasonal effect or the trend, things along those lines, you have 1,000 different numbers that you go ahead and draw from. And so what Prophet officially reports to you is actually just the 50th percentile of those 1,000 numbers.
And that's where we get the upper and lower.
Yes.
Kind of thing.
All it's doing is it's just grabbing percentile values from its simulated data.
Right.
Okay.
And then, so that iterative process you're talking about with the delta, so that it would go through that, and that would give it 1, basically, and it does that 10,000 times.
however many times you specify.
Yeah.
So actually, when you actually load it, when you set up a model in Stan, there is an argument called iter.
Uh-huh.
And it's typically anywhere from about 1 to 10,000, and that just sort of tells you how many times you go through this.
So like one run might minimize the delta at some parameter that it finds, and then another run might, depending on how it samples, like randomly samples the distribution, might find like another parameter setting minimizes the delta.
Rather, keep in mind here, you're not really minimizing the delta.
Or
you're just comparing the difference between your current draw and then your previous draw, and then you compare that to delta. And then basically, if the difference between the two is greater than delta, then the new draw becomes your new parameter value.
Right. But then that process ends when you don't meet the threshold.
Yeah. So the idea is what you actually want to do is give the whole process enough simulations so that way you get to the point where you're practically never going over this threshold again. Because the idea is you sort of converge towards the true distribution. And so therefore, after every single subsequent round, the difference is practically never greater than this delta, which sort of means you found the true distribution, whatever it is.
Yeah. And now,
an incremental iterative process. And so the idea is when you actually run a Bayesian simulation, you actually sort of want to make sure you've sort of converged towards the correct, towards the true distribution.
Gotcha.
So the idea is maybe if you have a messy data set or a lot of model parameters, you might need more simulations to kind of converge towards the true posterior distribution. But maybe if you have a simpler data set that's maybe more strongly driven by just a few effects, you might only need a smaller number of runs to kind of get at the true answer.
Right.
Yeah.
Yeah. Cool.
Good. All right. All right. So just a walk in the park, right, Devin?
Yeah, I totally get it.
Yeah. Actually, you're doing pretty good. Let's go into our notebook, all right, and then just recreate what we did the previous week. And then we'll upload the housing data set, and then when we're done, we'll take a look at how this works in Profit.
Cool.
And by the way, actually, Profit actually mostly makes fairly linear assumptions. So it's actually, it kind of is like, it's not exactly linear regression, but its underlying assumptions are fairly close to it. Okay, so let's do this. Import PyStan, import pandas, and then let's import Profit. Okay, and then go ahead and then upload the housing file. You probably already have it on your computer.
Yep.
All right, so go ahead and get that. All right, so load this in. Okay, so do you have this?
Yep.
Okay, all right, yeah. So the idea is, let's take a quick look. All right, this is what we did last week. So setting up these models in Stan is kind of alien. It's not, I mean, it's Python in name, but only in name only, because you actually set up all of your model parameters as a string. So here, Bayesian simulations are computationally expensive. And so Stan is basically almost pure C++. And it doesn't even use the Python interpreter. So it just sort of takes whatever you put here inside the string and then just
yeah, it's super weird.
Yeah, it's very strange. Actually, if you use Bayesian programming libraries, they actually work in a pretty similar way. So like other ones that are fairly common, there's one called JAGS, PyMC. I think there's one called Bugs too. I've never used that one, but most of them actually tend to kind of work the same way. So if you're familiar with this kind of thing, it actually, they all kind of work the same way. All right, but in any event, okay, so you define different aspects of your data. So let's do this. Okay. And again, this is kind of weird at first, but basically, whatever characteristics of your data that you're going to use to build your model, you have to define as separate variables over here. So in this case, we're basically saying M is however many rows are going to be in our data set.
Okay. What's that lower equals 0?
Basically, we're saying this number has to be at least 0. Like a data set can't have a negative number of rows.
Yeah.
You don't have to. I mean, in practice, you could omit this. It would still work. But, just as sort of a check. Okay, right? So basically, in this case, this number is basically going to be M. Right? So our data set is 506 rows, and then this number is going to be 14, N. Yeah, question?
Nope, makes sense.
Okay. All right, we also have X. And so the idea is X is going to be a matrix which has M rows and N columns. And then vector is going to be M. So Y is basically going to be, a single column with M number of values. Okay. Over here. All right. And so, okay, for what we're going to do, this is going to be it. Okay, so that's our data. Okay, now the parameters. So the parameters here, we basically have the intercepts, we have the coefficients, and then we also here, real quickly here, you don't have to sort of type along with this if you don't want to. All right, and then 1 second here. All right, so we'll go ahead. All right, so the idea then here, very quickly here, Devin, it's actually kind of an important aspect of linear regression. So if you do this, LReg predict X. Okay, so if you make predictions on X, you get these estimated values right over here. Okay, minus Y or minus. Okay, so this is your error column. Okay, the idea here, this number right over here is actually an official kind of parameter of a linear regression model, 4.68. Because the idea here, so if we do something like this, means I probably missing one over here. Okay, so the idea here, so these predictions, essentially what you're thinking is the predicted value of this house is basically normally distributed with an average value of 30 and then a standard deviation of 4.68. So the standard deviation of the error column basically tells you how much you could expect these values to go ahead and differ.
Right.
Okay, so it's actually in linear regression, the standard deviation of your error column is sort of kind of an official number that you incorporate into the model. Because it sort of tells you pretty much the size of the error bars on each of these estimates right over here.
So it's not a given though, right?
Like, no, it's not a given at all. Like you actually find that out at the end.
But does it depend on the parameters that you end up landing on?
Actually, it depends on your data, really, like how accurate your model is. That's actually something that you find out. Like that's basically one of the outcomes of the model fitting process is to kind of understand what that value is. Okay, but the idea is in the same way you want to figure out what your coefficients are.
Yeah.
You also actually want to figure out what that value is as well, because it'll essentially tell you how reliable these answers are.
And the point is that is the standard is it more important this like normalized standard deviation like versus the mean error? You know what I mean? Like because if you had a bad model, like it would, or the values you're looking at were really big, standard deviation would be a lot bigger.
That's true. No, that's actually true. Generally speaking, you'd want a smaller. It actually is kind of like a reflection of how reliable your model is and how good it is. Because generally speaking, like a better, more sophisticated model that better describes your data would have a smaller standard deviation associated with your predicted values. So it is a reflection of just like how reliable something is. So for example, here, this thing right over here, 11.52, this basically means that the predicted value of this house, if you think about the two standard deviation answer, actually varies significantly, right? It essentially sort of means the estimated value of this house could be anywhere from about 3 to 20.
Right. Totally. Yeah.
Yeah. So yeah, you don't define this beforehand, but the idea is it's actually a parameter that you solve for. Okay. The reason why I'm saying this is if we go down here, so when you specify parameters, okay, we're basically saying we're going to call the alphas what we're going to call the intercepts. Okay, n is the number of columns. Okay, and so basically here, this sigma thing, right over here, Devin, okay, is what I was talking about up here.
Right.
So the idea is, right, this officially kind of informs us of how reliable our predictions are, and it's something that you solve for. So therefore, you actually have to define it beforehand. Okay. So, right, we're kind of, basically, we want to figure out what that number is. Okay. And then we'll actually find here, so in normal linear regression, all right, we see here it's 4.68. You'll find out once we actually sort of feed this thing through the Bayesian simulator, it comes out to about the same value. But the idea is you don't necessarily know what this is. Okay.
Right.
All right. And then finally, you define the model. Okay, so essentially what we're saying over here is we are assuming our coefficients are normally distributed with mean 0, standard deviation of 1. This is somewhat naive in the sense that maybe we're not really making a strong claim on what we think they are. So we're just kind of starting off with something fairly innocuous.
But this still like limits the model to this parameter here? Like it's not going to try other parameters, right?
No, so what it's going to do, basically, this is going to go ahead and then determine what sorts of values are being generated from the sampling.
Mm-hmm.
Because so basically, when we first start off, right, when we're kind of taking a look at like, let's say the sample values that we're comparing, okay, what that means is the sample values for the coefficients are pretty much initially are going to be basically simulated from a normal distribution of 0 with an average value of 0, standard deviation of 1.
Mm-hmm.
It doesn't mean they're going to end up this way. This is kind of what we're going to start off with. Okay. If we're really not sure what they were, Devin,
yeah,
you could increase the standard deviation like that.
I see. Okay.
Which would kind of give you sort of a wider spread.
Right. So it's just started off.
I'm sorry?
It's just to start off.
Yeah, it's just to start off with, yeah. And then if you actually had a better idea of what these are, you could actually be more informed about this and be more opinionated.
And if you did that, would that just reduce the amount of time it takes, or would that create a better model?
Typically speaking, in terms of getting a better model, you actually want to make sure the distributional assumption you're actually generating the data from actually maps to what's actually generating the actual parameters themselves. So basically, if you think you have a normally distributed process, when in fact you have, let's say, a Poisson distributed process, that means you could actually just not have a very good model. Because a normal distribution, if you might not necessarily just sort of converge towards the same sorts of answers as a Poisson distribution or something different. So getting the right distribution is usually good for making sure you sort of get the right results. And then in terms of how fast you converge, that's usually kind of more determined by what you put inside the parentheses.
Right. Gotcha.
And so basically, if you're pretty sure you know what something is, you can actually be pretty opinionated here. Like, I'm pretty sure this has X, Y, Z values with it and things like that. This can be useful maybe if you don't actually have a lot of training data, but you're pretty sure you understand what these things are. So therefore, even if, you don't really have a lot to work with, you can actually start off with a pretty informed estimate of what you think things already are. Or likewise, if you have absolutely no idea what they are, like you're just totally clueless, assuming if you have normalized data, you can do something over here, right? So like, average value 0, standard deviation of 10, that's extremely wide. So this is sort of like saying, I'm pretty sure these values are normally distributed, but I actually have no idea what they could be.
Yeah. So maybe
this also means, real quick, this also means though, it could, because the range of values you'd be sampling from would be that much larger, it could usually take longer times to converge towards the correct answer.
Right, right. And this is talking about the distribution of the coefficients, like
it's correct.
Because linear regression is the assumption of a normal distribution of your data.
Correct.
Right. So, but this isn't saying like if you did Poisson here, it's not saying your data has a Poisson or like a non-normal.
Your coefficients are normally distributed.
Yeah. Yeah. Okay. Cool.
Yeah. No, you make distributional assumptions about your model parameters more so than your data. Okay.
Yeah.
Okay, so we have this right over here, and then the idea is why, and this is what we were talking about before, we could say this. Okay. This is vector notation for just sort of saying simultaneously take every single column in X, multiply it by every single corresponding coefficient, and then add in the intercepts. This is matrix notation for saying, M1 X1 plus M2 X2, M3 X3, and things like that. Okay, because the idea is, okay, so we define X like this. Okay, and then, when you're done fitting linear regression, you have coefficients like this right over here. So the idea is, if you do this, it sort of performs the column-wide operation simultaneously all at once. Are you with me there?
Yeah.
So basically, if we wanted to, we could do something like this. Say, take this column right over here and multiply it by this, and then take the column at position 1.
I see what you're saying.
And then, basically take every single column and then multiply it by its corresponding coefficient. But most data science libraries are designed that if you just kind of take the whole thing, it'll just do it for you simultaneously. All right. So the idea is if you do this, okay, and then you actually, let's do this something like this. So the idea is if you do this, right, and then all right, and then do this right over here. Okay, this gives you, this is sort of saying like, M1x1 plus M2x2 plus M3x3 plus M4x4. And then, right, and then you add in the intercept. So basically,
because they have the same shape.
Yeah, exactly.
Yeah.
And then you add in the intercept at the very, very end. So in a lot of ways, the thing about this, we're sort of saying x times our betas plus the alpha, and that's kind of what we're doing right over here like this. Okay, and the same thing, we take sigma and then put it in here like that.
Gotcha.
Okay. So this is basically how you define the model. Okay, and then let's do this. Okay. So this is really just loading this stuff right into Stan. And then let's hope real quickly here. Notice here I put the semicolon right over here, Devin. Okay, let me do that. All right. So this just kind of loads this into Stan. And then the idea then I forgot one thing. Hold on. So real quickly, you know how we kind of define these aspects, M, N, X, and Y for our data?
Right.
Here you actually have to sort of assign something to that. So we have M right over here, which is the number of rows. Right? So it's that number right there.
Right.
Okay. And then likewise, right, N would be the number of columns. Like that, right, X. We actually just make that X, and so Y would be, that's actually really important because this is what we actually use to generate samples from the likelihood. Like that right over there. Like this is actually what sort of informs sort of the evolution of our model parameters and actually kind of pushes them in a direction that's fitted to our actual data.
Right. Yeah, because just a generic.
Yeah, because basically, if we didn't actually have something like this, and we were just constantly sampling from these distributions, like it would actually not go anywhere. Like it would just really wouldn't. It would just kind of stay the same because it's not really the actual samples that we have in X are actually kind of what causes the difference between like one iteration and the next to kind of allow it to converge towards something that's useful. Okay, so in any event, all right, so you define the model, which is right up here, and then you feed it in. And then sampling, okay, this is where you actually pass in the data that you're going to use.
Right.
Okay.
One quick thing, I have to go at 8, which is in about 9 minutes.
Okay, sure. All right, no problem. All right, let's just do this right over here. Okay, and this is basically how many simulations we're going to go ahead and run. Okay. So just run through this. And then where? Okay, hold on 1 second. It's a dictionary, so we have to use these things.
Also, did we define X? Yeah.
I defined X.
I guess
if you didn't, you'd want to go ahead and define it now. It's just everything except the price column. All right, parameters or transform parameters cannot be.
How'd you fix the last error? Oh, I see. It's yeah, right.
Like that, right over there, and then actually, let me check. And then let's try this. Okay, here we go. Real quickly here, Devin, where it says parameters.
Mm-hmm.
Okay, make sure it's a real number, not an int. That was a mistake on my part.
Oh, I see.
Okay, and then it'll take a little while to run.
Yeah, cool.
Okay. All right, yeah, so this is pretty much, we're just kind of defining everything inside, the Bayesian formula.
Mm-hmm.
And now sampling just means exactly that. It's sort of just generating it's basically, randomly generating values from these distributions, plugging in the numbers, and then, comparing the difference between, the current draw and the previous draw. And then if it is above the standard threshold, which I think is 0.1, then it'll update the values here like that. And then, so give it a minute. And so big thing over here when you're done. All right. So sort of the idea is, right, so all of our different parameters right over here, right, this is sort of telling us, the different percentiles of what the actual values are. And this is based off of our simulated draws.
Mm-hmm.
Okay, and so typically, when we sort of report point estimates for something like the intercept or things along those lines, it's really, the idea is actually, it's the 50th percentile of whatever these things are.
Right.
But the idea is Bayesian methods kind of give you a better feel for the true range of values, you might be able to expect. Okay. All right, so we have 6 minutes. Okay. Let's take a look. Import profit, so do this. All right, ready?
Sorry, 1 second. For importing, is it just import FB profit?
Yeah, right over here.
Oh, I see, yeah, okay.
Like that, okay, and go ahead and initialize it.
Oh, shoot. I think because I set up a new environment.
Oh, okay, it's not there.
Oh yeah, it's not here.
Okay, it's fine. We just have 5 minutes left. The idea is this is basically what profit is doing when you call fit. So here, real quickly here, if we just have 5 minutes, I'll just kind of walk you through a few things, okay? All right, so when you initialize profit, so take a look over here. So this thing we have here called SM. Okay, so let's take this. When you're done doing this, there is an attribute called model code. And so if you print this, you'll see this is basically what we set up before. Okay, like that's basically what's stored inside over here. So when you initialize profit right over here, there is an attribute called stand backend. This is basically literally how it incorporates stan.
Yeah.
Okay, model code. It's a bit more elaborate.
Oh, wow. That's cool.
Yeah, and so this is actually, so when you actually call fit, right, and it's generating, your different distribution, your simulations and things like that. Okay, this is the actual stand code that's being used to generate it. Okay. Yeah. And actually, when you see these things right over here, so like 4i-1t-yi, so basically, because it's time series, it's actually generating the value step by step versus all at once. So it's sort of figuring out, like, the trend and some of these other values at every single individual time step. And then just kind of going through these things. It's actually, most of these things are actually normally distributed. So it actually doesn't get too far away from linear regression. And it's actually just the same thing that it's, in practice, it's very similar to what we just did, right? Where you kind of set up there are more parameters, because there are things like, for, seasons and holidays and, all the sorts of different time components and the trends and things like that. But it's all effectively set up in the same way. Where you have, right? So we can see this, right? There are different, coefficients for the different time parts, and then the trend, and then all these sorts of things. Right. And then you just kind of go through over here, and then you specify the distributional assumptions and how they're generated and things like that. And it just generates the samples. So real quickly here. All right, this is probably something you're not going to be able to follow along with, but I'm assuming you don't have stand on your computer like right this instant. So when you call fit on your data, okay, this is the source code. So this dictionary over here called DAT, okay, this is basically this thing.
I see.
Right over there. Okay, so it takes your data set, pretty much, takes different characteristics of it, and then stores it right over here, and then just passes it in to, this right over here, and then just sort of goes through the corresponding simulations. And so real quickly here, so this right over here, Devin, really is kind of the underlying code that's used to generate your actual predictions right over here.
Yeah.
All right. And so real quickly here, we'll just kind of cap this off with something. All right, let me go ahead. Blah, 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 blah. We should get over here right at 8 o'clock, all right?
Okay.
All right, so understand here, you're probably a little bit of a time budget. All right, so then we do this. Let's find CSV file. All right, so we'll do this right over here. I understand you're just watching, but it's what we have for now. So, all right, so we'll do this. All right, so here's our time series. Okay, and so literally what it's doing, right, it's just sort of taking the values defined in this thing right over here, that variable right over here. And so, and it's literally just sort of passing it in. This thing, mod, this thing right over here is literally this thing.
Right.
Right. Yeah. And so then, this is actually hidden, like this is not made publicly available right over here where it says that. But essentially what it's doing is it's, when you call fit, it basically defines this variable and sets up, all your different data parameters. And then, it calls sampling right over here, and then data is equal to, this thing right over here. And then that's pretty much it. And then real quickly here, and then the actual samples that it generates, we'll give this a minute, and this will go ahead and then wrap up the class. It lets us fit. Okay, so here are all of our different components. All right, it only gives us 2 of them right over here. But the idea here, if you look at y hat, all right, so the shape of this, right, is 2,905 by 1,000. The default number of iterations in profit is 1,000. And then the data set that we just loaded in right, is 2,905 rows long. So essentially, it's generating 1,000 different samples for every single unique time step. And then the idea is, if you just kind of take the 50th percentile of each of these, that's basically your final prediction.
Cool.
I think give us the correct answer. Okay, and then I'd want to set this up a slightly different way, but that's basically it.
Yeah, cool.
Yeah.
All right. Well, yeah. Thanks so much. This is
really
cool. Yeah.
No worries. Yeah, I think this probably scared off some other people. I think. Yeah. Usually, it's not quite this dense, but yeah. So we're gonna I'm going to take the month off, and then in the new year we're gonna sort of start off with a new rant. So we'll be done with profit, and then we'll go on to something else.
Cool. That sounds great.
Yeah. So thanks for coming, Devin.
Yeah. Thanks so much. This has been amazing.
Yeah. Good. Well, glad you enjoyed it. Good chatting with you. I won't keep you any longer if you have to be done at 8, and I will talk to you later. Okay.
Great. Okay.